That's funny. Okay, so we're going to look at exponential functions today. So our objective is to graph some exponential functions and to apply exponential functions to compound interest. You say no. So here's a question for you. Would you rather have $300 added to your savings account each year or have it earn 3% annual interest?
How much do I have in my bank account to begin with?
Right. Okay. So the answer is going to depend on the amount invested or your principal, P. Okay.
Is it 3%?
Do what?
3%. Unless if it's like
It's not.
Is it 3% of what you have in there?
It's 3% of what you have in there.
So if you
Well,
have
theoretically,
$100.
that number will continuously go up.
Theoretically,
So
it
at a
will.
certain if you do it early enough, at a certain point, it's gonna surpass that $300.
Right.
$300 might be more at the beginning, but at a certain point, it's gonna pass that.
This, especially
Right.
say you already have $1,000 in there, then you're going to be getting 3% of 1,000.
Mm-hmm.
Then it's going to get there even faster than the 300.
Right. Okay. So it's going to depend, like you're talking about the amount that you have in your account already and the duration of your investment. So T for time. Okay. So very good. But here's the deal. Like this is what we have to think about with exponential functions. Okay, those are things that we're using when we're investing money in a savings account. If you're deciding between putting it in a savings account, investing it in a CD maybe, or a bond, or a life insurance policy, or what?
For shirts.
Or shirts, yeah, because they're not paying anything back to you. Um, or if you're going to invest in the stock market, all of those different things. And some of them are more predictable than others, right? Like the stock market is not very predictable. You have to be willing to take the chance there. Um, so we can have exponential functions are a function in this form of y equals bx. My pen is not working, so let's try again. Okay, and we would call this a parent function as well when we get a little further on. So what do you, so it says where b is greater than 0 and b is not equal to 1. So we never want b equal to 1 in these. What do you notice about this exponential function?
It's gross.
It's gross. Why is it gross?
Because it's math.
That's not why it's gross. 4 plus 4 is math, but that's not gross math.
It is. The x power.
The x power, right? Our exponent is the variable. So that's got a little bit definitely different than anything we've ever had. Okay? Because when we had linear functions, there were no powers. Okay? When we had quadratics, the power was always squared. Right? We had a squared power, and then we had a power of 1, and then we had a constant. Now exponential, okay, we have an exponent that is our variable. So we can have an increasing exponential function or a decreasing exponential function. Okay, those are right here. Okay, an increasing function is when b is greater than 1. So the value of y is going to increase as x increases. And it increases, what is exponentially? If I say it increases exponentially, what does that mean? Consistently, because it has an exponent. Okay, when we say it increases exponentially, it's like super fast. Okay, because it's being multiplied by the power. It's raised to the power of itself. So instead of, so like the cubes would be increasing exponentially, right? If you looked at the cubes are 1, or the squares are like 1, 4, 9, 16, 25. Like they're increasing, like, right? And the numbers are getting further spread apart. And then if we go even higher than that to the cubes, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So we're going a lot faster. Okay, so our growth is it's exponential. It's increasing really quickly. If we're decreasing, it's the same thing. It's decreasing really quickly, but this is when our b value is between, so maybe this will help when we think about this, Brandon, because we had a problem like this before. When our b is between 0 and 1, okay, then it's a decreasing function. So it's going to be a decimal or a fraction. Okay, so that's when we have a decreasing exponential function. Yeah. Well, 0.999999999. Correct. Okay. Now, the next step. The closer the base, or b, is to 1, the more gradually the function increases and decreases. So if this number is 1.1 or 0.99, okay, it's going to be closer to, it's going to be more gradual. That was a bad throw.
Yeah, I'm a bad shot.
All right. Then an asymptote. How many of you have ever heard of this before? Not in Algebra 1?
Not
Okay.
in
So,
different contexts.
an asymptote is a line that a graph approaches but never intersects.
Isn't acetone like poison frog?
It's like a poison frog. That's a good call. Yeah. It's like a rattlesnake. You know, you can get close to it, but you don't want to get close enough where it can
I was
you
saying
touch
it's
it.
like an acid toad, like a poison.
Oh, acid toad. Yeah, I like it like a poison frog. Okay. Yes, you can think of it like that. It's like an acid toad. I like it. It's like a poison frog. Okay, so it says it's the x-axis is an asymptote in example 1. So if we look down here, you can see where these graphs come really close to, but they never actually cross that x-axis. That's because that is an asymptote.
It's on it. It looks like it. In fact, it looks like it goes across.
Starts
Nope.
on the x-axis.
It will look like it starts on the x-axis. It is true, but it does not.
It's on the x-axis.
It does not.
It's
I mean,
just coming impregnating in place.
because if we look at, yes, it does come really close. Because like we're gonna look at some of the graphs, it's gonna be like 1/27th, one, like
Oh.
over 268, like it, but never actually hits.
Piece of paper in between that line and that axis.
That's not how it works.
That's how it works.
That's not how it works. Because like there's also like nanometers, right? Like you can take a microscope and you can take really super like a microscopically thin shavings of things. Like it's not how it works. I know. But you will never, because here's the thing. If you can keep putting numbers into the formula forever and you're never going to get a 0. Like it's never actually going to be 0. It's always going to be a fraction or a decimal, just a hair bigger than 0, down to like the smallest number, but you're never going to hit the axis. It's going to look like it when you graph it, but it's never actually going to do it. So you just kind of have to accept that, yes, it looks like it's at 0, 0, but it's not actually ever touching the 0, the x-axis. Well, when we start to look at these, you'll see why. Okay. Do what? Yeah. Right? Just take my word for it. Just trust me. That's all you got to do, right? Just trust me. Okay. So for example 1, it's really hard to see here. So hopefully, okay, you can see, that's what I say. Hopefully you can see on your own paper a little bit. I went ahead and put all the stuff in there because it says graph the exponential functions y equals 2x. So that's the first one here. And we've plugged the numbers in. Y equals 3 to the power of x. Y equals 1/2 to the power of x, and y equals 1/3 to the power of x. Okay, and so then we put in an x. So there's a column for each of these, and we use -3, -2, -1, 0, 1, 2, and 3 for each of our x's, and plugged it into this equation. So we could then graph it. But what did we have to do first before we could graph it? Listen to Mrs. Talbert's lesson. Okay, we had to make a table. And it wouldn't have to be a table necessarily, but the big thing there is you have to plug in values for x. Okay, to solve like in that table. So then what can you tell me if we look at the graph, okay? This one over here, okay, is labeled that this is the y equals 2x graph. Pardon me, 2 to the power of x. Okay, where this one is y equals 3 to the power of x. What can you tell me about the difference between those? The number. Okay, which one is like steeper?
Well, it'd probably be
The 3?
Is the bigger the number steeper?
Okay, well, and so that's what I was going to point back to. Remember, if we go back up to when it says increasing function, when b is greater than 1, it's an increasing function. And then the closer the base b is to 1, the more gradual it increases or decreases. So it's more flat.
Y 3 to the power of x.
It's flat.
Okay,
The flat jack.
so this one, y to the power, or 3 to the power, y equals 3 to the power of x is like the steeper one. Okay, it's going up more quickly. All right, then if we look at the 1/2 and the 1/3,
I went down a water slide that was at the steep ones.
what do you notice about those two? That's y equals 1/3 to the power of x.
Pretty gradual, right?
But they're the same graph.
With a decreasing function. Measured out. What it means?
Is it not
Okay.
the same graph?
What do you mean is it not the same graph?
It's mirrored.
It does look like it's mirrored. Okay.
It is mirrored.
Well, because it is mirrored, okay. What's it mirrored around?
0, 1.
The y-axis.
The y-axis, okay. It's mirrored across the x-axis here. So which one is mirrored to y equals 3 to the power of x?
The 1/3.
The 1/3 exactly mirrors that, right? Which one mirrors y equals 2 to the power of x? Or, yeah, the 1/2. Okay, so this one here, okay, is perfect mirror of the 2 to the power of x. Good. Okay, now, Brandon, coming back to your question, what were you saying?
I don't know.
Okay. You said you thought they look like they're the same graph.
They are though.
What do you mean by they're the same graph?
Like it just continues across that axis, so why
It does not. So like the purple one is like this one. It's right along there and it goes up to here.
Yeah, but the points are on the same spot.
Okay. The pink one is pretty close and it comes up here. And then the next one, it starts up here. Ooh, it didn't change color on me. Let me try again. Okay. It starts at, and it's crossing over to the other side. Whoops.
It did cross.
It did cross the x-axis.
Liar.
Dang it. Human error. And this one comes this way. So do you see, does that help you see that they're not the same?
Why are they, if they're the same, then why are they numbers on one side and fractions on the other?
Because he's saying why are they whole numbers to get them on the right side, but then they're fractions to get them on the left side?
Is that what you're...
Or no.
Like if they're the same thing, just going the opposite direction, then why is it not whole numbers?
I think I know what he's saying. But so like, so the outermost, so if you look at the, wait no, pink is that 3 to the power of, is that the right one?
Yeah, pink is the 3
That doesn't make sense. Wouldn't,
to the power of x.
Well,
yeah, why does the fraction get them on the left side?
If the higher number is steeper, then why is 1/3 steeper than 2?
Okay, so if the higher number is steeper,
1/3 is less than 1/2.
Yeah.
mm-hmm,
So it makes sense because 1/2 is closer
Because
to 1.
3 is steeper than 2, but 1/3 is steeper than 2. But
Okay.
2 is a higher number.
Okay, so it is because of your exponent. Like if we, and that's, I see where you guys, I think I see where you're struggling. So like we have our exponent is -3. So if we break this down, 2 to the -3 power. Why is my pen going crazy today? Okay, let's see what we can do here. So 2 to the -3 power is the same thing as 1 over 2 to the 3rd. That negative exponent automatically makes it a fraction.
Okay.
Okay, so then this is 1/8. And then if we have, so like 3 to the -3rd power is 1 over 3 to the third. Okay, so that's going to be 1 over 27. Does that make sense a little bit more? Like it's that negative exponent does turn it, the negative means it needs to be in the denominator. We've talked about that.
Okay, so since we're starting out with a whole number, the negative changes into a fraction.
Correct.
But if we have a fraction to begin with, it changes into a whole number?
Okay, so let's look at that. So if we have negative, or if we have 1/2 to the negative third power. Yeah, how would we do that?
I don't know. I put it in my calculator, that's how I do it.
You put it in your calculator.
Then the negative exponent I put in the denominator, right? So it'd be 1/8, or is that wrong?
It'd be, so this would be saying like the -3, so the 2 is in the denominator, the 1's in the numerator, it would flip. So it'd be 2 cubed over 1, which is equivalent to 8. Okay, where the 1/3 to the negative third is now 3 to the third over 1, which is the 27.
So that's why, because it's a negative number, so that's why it's steeper.
Oh, wait.
Because you flip the fraction itself when you're, so if it's to a negative exponent, you flip the fraction and then plug in the exponent to the top of the thing. Okay. Yeah, so it makes sense.
Okay. Looking at the rest of the table, I'm making more sense.
Okay.
Because I was just looking at the graph.
Right, and I get that.
The table yet.
And that's like, this is one of those examples. I felt like if I just put the work up there, we could have better conversation instead of like calculating it and trying to graph all 4 of them.
So the exponents on the left side, for like those fractions, are always going to be negative, and on the right side, it's going to be positive. Or does the, so that like the x value, does the x value change at all?
Yeah, you get to pick the x value. Like that's what you're putting in the table, is you're choosing the x values.
Okay, but when you plugged in -3, it's -3 for all of the places. Okay, I see. Okay.
Yeah.
It's still a little.
Okay.
I think I get it now.
Okay. Because like if you can make the table and do the math, and like if you plug it in your calculator and get it out, that's fine too. But like making the table and like making the graph is going to be kind of key to being able to work with exponential functions.
As long as I put it in my calculator.
Yeah, as long as you put it in your calculator right. Right, you have to code it correctly there, otherwise it's not going to do you any good.
I had a really annoying operator error the other day.
Did you figure it out?
I did eventually figure it out, yes.
Good.
I was trying to get my, so for the longest time, my PS4 wasn't working. So it was saying that certain actions couldn't be used.
So then the next part of this is like, so these were all considered parent functions. They all followed that format y equals b to the power of x. So they're all considered parent functions. Okay, now we can start, Brandon, are you with me? Okay, we can start changing the function and adding to it, okay? And so we can transform it if we start looking at the function like this. So how is this equation different than the first equation? What are some other things to it? Okay, there's an a. Okay, let's look down here and find our a. See, we have h's, k's. Here is our a's. Okay, so when the absolute value of a is greater than 1, the graph is steeper than the, okay, we're comparing these to the parent. Okay, so if we change this, and so if we take that y equals 2 to the power of x and make it y equals greater than 1, so let's say 3 times 2 to the power of x, we're going to make our graph steeper. Okay, or if we make it a is between 0 and 1, so y equals 1/2 2 to the power of x, it's going to be a flatter graph than the parent function y equals 2x. So oftentimes when we're doing these, we're going to graph the parent, and then we're going to make some changes to it. Okay, what's another letter a variable that you see that's different or new? B was in the parent. Yep. Okay, so let's look at the H first. Okay, if we look at the H.
This is going to be one of those confusing things where if it's negative, it's actually positive.
It is. That was what I was going to point out because we have x minus h. So if it's negative, it's actually positive in things. Okay, so our h's are here. H tells us if we're translating it right or left. Okay, so it's a right or left. Whatever the number is. So if we say it's x minus 3, okay, so this is a positive h, right? So if h is greater than 0, I just translated this.
Like 3 points to it?
3 units to the right. Yep. Versus if I would have had x plus 3, I would have went where? Because this is actually to the left 3. Okay. All right. And what's another variable that we see that's new? The k is new. Okay, and the k's are here. They tell us if we're translating up or down. So if I say plus 6, how's that translating that one? Up 6. Okay. What if I say minus 6 here? Down 6. Okay. Because here's the thing. All of these adjustments are just translations of the parent. What does a translation mean?
It's like you're changing it from one form to another, like from one function.
Okay. What'd you say? You're just moving it.
Yeah, I thought you meant like the definition of what translation is. Because I was also thinking like a translator, like language.
Okay, nope. In mathematical.
Just talking about this?
Yeah. We're just moving it. So if we had, say we had a box, a rectangle, here. Okay, maybe that was our shape, and it said we translate it 3 units to the right. Okay, well maybe that puts it right here. And then it said translate it 4 units down. Well, that puts it like right here. All we're doing is moving it. But this one is our parent. The first one is always our parent, or the one that's in this original form. The nice thing about that is when you get these really complex looking equations, like example 2, or this function, g of x equals negative 3 over 2 times 2 to the power of x, you don't, actually that one's not too bad. It's more on the back side that we have one that's really complex. We don't have to do all of the stuff. Like we don't have to solve all of the hard stuff. We really just need to make a table for the parent function and graph it and then do the translations. It's way easier. Uh-huh.
So, because we figured out how to move all the others. So, how do we know how much steeper or how much flatter 8 is?
Okay, so when we solve these, we will, I'm going to show you in example 2. The steepness and the flatness, we do have to kind of take a, b into consideration. The h and the k, after we solve for the ab part, ab to the power of x, then the other things, we can just move them around.
Okay, so a is one we have to like solve for.
Yes,
Okay.
We'll have to include it.
So
Yeah.
that's the thing that I was most confused over. Like, how do you know how much steeper, how much shallower?
Yeah.
Flatter, I guess.
Yep, nope, that's one we have to really kind of solve for. So let's look at it with this example 2. It says graph g of x equals negative 3 halves times 2 to the power of x as a transformation of the parent function f of x equals 2 to the power of x. Then describe g of x by stating its domain, range, y-intercept, and the equation of any asymptotes. So there's a lot happening there. What's the first thing we need to do in order to graph these? A table. Good, we need to table it. So we'll do negative 2, negative 1, 0, 1, and 2. What do you think would be easier to graph or to table first? The parent function, f of x, or the transformation, g of x? Parent, okay, so we're going to do the parent function first. So the 2 to the power of x. And then we'll do the transformation, which is the negative 3 over 2 times 2 to the power of x. So for our first one, when we put x is negative 2, we're going to have 2 to the negative 2 power. Well, that's the same thing as 1 over 2 squared, which is,
Wait a minute. Oh yeah,
because it's a negative,
1/4.
it'd be 1/4. So then what's our next one going to be? 2 to the negative 1.
Which is 1 over 2 to the first, which is 1 half.
Awesome. Good. All right.
0, anything to the power of 0 is 1.
Anything to the power of 0 is 1. Okay. What about anything to the power of 1?
It's the same.
It's the same, right? It is itself. Those are always nice.
2 to the power of 2 is 4.
Okay, so let's go ahead and graph our parent function. So we're going to have negative 2 and 1/4. So it's close to that axis, but not touching it. Negative 1 is a half. 0 is 1. 1 goes up to 2, and 2 goes up to 4. 1, 2, 3, 4. Okay, so then I'm going to extend that line so it's kind of almost flat against that x-axis, but not quite touching it, and then it gets really big really fast.
Touching it, but not.
Touching it, but not touching it, right? Touches it in real life, but imaginary life it does not.
I could just imagine. I imagine like the annoying kids are like, I can't get mad.
Yes, that's exactly it.
Get mad. I'm not touching.
I'm not touching you. I'm not touching you. Like with their
Exactly.
finger right there.
Yeah.
I'm not touching you. And you just want to like slap their finger out of there,
Yep.
right?
No, actually, I just slapped them.
You just slapped them. Okay. Now,
Right across the face.
the cool thing that because you did the parent function first, right, is that this has the parent function. Why are my colors not changing? This has the parent function in it. So when we do negative 3 over 2 times the 2 to the power of x, we could just say, oh, that's times 1/4 here. To be like, oh, that's negative 3/8. So it's going to make it a little bit easier to solve because you did your parent function first. So 2 to the power of negative 1 here is 1/2. So we're just going to say, well, negative 3/2 times 1/2 equals what?
2. Wait.
What is it?
Negative 3/2 times 1/2.
Negative 3/4.
Negative 3/4.
Sorry, I don't know how to do fractions without a calculator.
You multiply straight across. That's it. 3 times 1 is 3. 2 times 2 is 4. So for the next one, we're going to have negative 3/2 times 1. That's just negative 3/2. Now we've got negative 3/2 times what? Times 2.
Which is negative 3.
Negative 3. The 2's cancel. Because this would be 2 over 1. You could look at it like that. Huh?
Your answer's 4.
Oh, I'm not quite down there yet. I see what you're saying. Because I got off. Negative 3 over 2 times 4 equals what? Anybody agree with negative 6?
Sure.
Doggone it. I don't like sure.
Well, it's what you got.
Okay, and so we can graph that. This time at negative 2, we're going to have... See, and I don't even like graphing those numbers. I'd rather start here where I can have some whole numbers and have an idea of what's happening. So you could start anywhere. Like, I'm going to start with 1, negative 3. So I'm at 1, negative 3, 1, 2. 3. And then it was 2, negative 6. 1, 2, 3, 4, 5, 6. And then I'm like, okay, 0, negative 3.5, so negative 1.5. Negative 3/4 and negative 3/8. It does look weird. Yours probably looks better. What's it reflected across this time? The x-axis. Why? Why is it reflected across the x-axis?
Because math.
Not because of math.
Because of the
Oh,
reflection
A
rule
is
right
less
there.
than 1.
Less than 0.
That's what I meant.
Okay, when A is less than 0, it reflects across the x-axis. The others, right, they were the parent function, so they weren't really connected to each other, but they looked like they were reflected across the y-axis. It appeared. All right, so now we get to do all the other fun stuff. Okay, we're stating the domain, the range, the y-intercept, and the equation of any asymptotes. But this is for g of x. Okay, we're looking at those. So first of all, what's the domain of our g of x?
G of X is negative.
The domain. What x values?
-2, -1, 0.
Nope. We want all of them. Like this is just a sampling. We made a table so we could graph it. What are all of our possible domain values?
Oh, X. It's just, was it all real numbers?
It is all real numbers, right? Because they can keep coming back here. So it's all real numbers. What's the range? It's getting closer and closer and closer to what? 0.
Anything less than 0?
So it's y such that y is
Less than 0.
less than 0. Good, because it's below. Very nice.
So that's just the first section equation.
Yes, we're only describing it for our g of x. We're comparing it. We can, yep, we're only doing our g of x. Okay, how about the y-intercept?
Is
1 and -1. Oh, just -1. Sorry, just 0, -1.
it's negative 3/2.
Okay, so 0,
Oh yeah.
right? 0, negative 3/2.
It wouldn't put -1 on the chart. I was just looking at what it said on the chart.
Okay. And the last one is the equation of any asymptotes.
What are they?
The asymptote, it's the line it's close to, but it's not crossing. It gets right up there. You might even draw it where it looks like it's touching it, but it's mathematically not touching it. It's both of those things?
You said the equation of what, the line?
Of the asymptote. The asymptote, it's the line that the graph approaches but never actually intersects. Okay, the x-axis, but that's not an equation. What's the equation for the x-axis? Not y equals x. Nope. Y equals 0. It's always the opposite of what we have. So the y equals 0. Okay, and I won't see you guys next week, like I said, because of ITBS testing. But we did not make it through.
So no homework.
No, you do need to do some practice. Yeah, huh? Yeah, huh?
Leave.
1 through 11. Odd. Should take care of it.
What was it?
1 through 11, odd.